In the last video, we introduced Riemann sums and used it to calculate the integral of x squared from 0 to 1. That was only a warm-up. To familiarize yourself with Riemann sums, we are going to see a more advanced use of it. Here is the Riemann sums formula that we derived last video. You can see the derivations in more detail in the last video. For this video, we are interested in this integral. That means we can set a to be 0, b to be pi over 2, and f of x to be the sine function. We then calculate delta by simply substituting a and b into this formula and get it to be pi over 2n. Then by using this Riemann sums formula, we substitute a, delta, and f of x to get this expression. But now what? It is possible to do this algebraically using trigonometric identities, but we will use geometry instead to solve this limit, which actually illustrates the solution more naturally and beautifully. I highly encourage you to pause the video and try interpreting this limit geometrically. The key to calculating the limit is to realize that there are two interpretations of pi over 2n. The first one is about the angles. We divide a right angle, which is of size pi over 2, into n equal angles. The second is the length of an arc. We are talking about this bit of the circumference of the unit circle here. The arc length part is actually based on the definition of the radian measure. Since we are using a unit circle, the radius is 1. So the angle and the arc lengths are the same, and so if the angles are of size pi over 2n, the arc lengths are also of size pi over 2n. Okay, but how does knowing the two different interpretations help us with the limit? Now, the argument of the sine function in geometry can only be an angle, so these pi over 2n will correspond to the interpretation as an angle, while the pi over 2n in the white box will correspond to the interpretation as the arc length. What remains is the interpretation of the sine function. The definition of the sine function is that if we measure an angle from the positive axis counterclockwise, then if we now say the point A corresponding to this angle has x, y as coordinates, and that we are working on a unit circle, then sine theta is defined to be the y coordinate, while cosine of theta is defined to be the x coordinate. Alternatively, you can also say that sine theta is the length of the vertical segment, and cosine of theta is the length of the horizontal one, up to some sign changes. Now, in this diagram, the angle here is some multiple of pi over 2n, where k is between 1 and n. And so this vertical segment has length sine of k pi over 2n, according to the previous discussion on the definition of the sine function. So now we are ready for this diagram and finally be able to interpret this limit. Let's say we want one term in the limit. Firstly, correspond the sine part with the vertical segment, then correspond the pi over 2n with the arc length. But no, I am not talking about the area of this strip here. Just think of this as an abstract product of some sort. We will associate something more concrete to this product later on. Consider this diagram. The region bound by B, C, and D is not exactly a triangle, but as we get n higher and higher, it will be closer and closer to a triangle, as the arc becomes closer and closer to a straight line segment. Now consider these two angles, which according to the sum of angles in a triangle should add up to a right angle. At the same time, the sum of these two angles will be approximately a right angle. This is because in the limiting case, the arc will be extremely close to the tangent at B, and we know that the tangent and the radius are perpendicular, and so we have these two angles summing up to something close to a right angle. The approximation sign is in the sense that in the limiting case, the sum would equal a right angle. Combining the two relations, we have red angle approximately equal to the yellow angle. Again, we mean that they will be equal in the limiting case. Because of this, we can conclude that the sine of red angle is approximately the sine of the yellow angle. This is because the sine function is continuous everywhere. To figure out sine of the red angle, we first take a look at this triangle. We can see that it is DC divided by BC. Although BC is still an arc, it will become a straight line in the limiting case. What about sine of the yellow angle? We have already established it should be the vertical segment AB. The most amazing step now is to multiply both sides by BC and we get this relation. Why is this amazing? Remember that AB times BC is the so-called abstract product we have been looking for. And now we have transformed it into something more concrete, the length of DC. What I like to think is that this product is the projection of the arc BC onto the x-axis. Notice that the limit wants us to sum up all the products of this type. By running the same argument, these products are also projections of the arcs onto the x-axis, and the sum of these projections is just 1. That means the integral of sine x from 0 to pi over 2 is just 1. Let's just review what we have done to achieve this. Firstly, we rewrite the integral in terms of Riemann sums. Next, we interpret the limit as the sum of these abstract products. Then we find out that these abstract products approximately equal to the projections of the arcs. Finally, we sum up these projections. Among these 4 steps, only the first step is not that elementary, and others do not require advanced concepts. The best thing about this argument is that you can generalize this easily to calculate the same integral with different lower and upper limits. I won't show the exact details here, but consider this diagram with A and B as angles. Again, we can consider the projection of the arcs onto the x-axis. The right segment here is by definition cosine of A. And similarly, the left segment here is the negative cosine of B. The reason we have the negative sign is that the cosine of B in this case is negative, and so we need a negative sign to make it positive. That means we have proved this formula that is typically derived using integration. Of course, I have skipped a lot of details here. So one of the challenges that I want you to take is to fill in the gaps, namely, why we consider the projection of that arc, and whether we can extend the argument to other quadrants. The second challenge is to see whether you can prove a related integral using a very similar argument presented in the video. Leave a comment to see how far you've got. If you enjoyed this video, like and share it and subscribe with notifications on, and see you on the next video. Bye!